Hi all. Today we are going to discuss about the action potential in a cardiac muscle, that is both atrial and ventricular muscle fibers. Before going to the topic, we should understand some basic points. That is, cardiac muscle cell or myocyte is polarized, that is, there is an electrical voltage across the cell membrane. In a resting cell, the membrane potential is called resting membrane potential. And we say that during resting, a cell is polarized. That is, it is more negative inside. And we should also understand that at this resting state, there is a concentration gradient for ions like sodium, potassium, calcium, etc. That is, for example, sodium and calcium concentration is more outside of the cell when compared to inside. So there is a concentration gradient for sodium and calcium across the cell membrane. So because of this concentration gradient, we can expect movement of sodium or calcium from outside to inside, that is from higher concentration to lower concentration. And this movement takes place through the channels, that is sodium or calcium channels present within the cell membrane. And this movement is known as influx, sodium influx or calcium influx. Influx means coming towards the inside across the cell membrane. So like this, concentration of potassium is more inside when compared to outside. So we can expect movement of potassium from inside to outside through the potassium channel present within the cell membrane. And this movement of moving outside is called potassium efflux. With this basic idea, we'll move on to phases of cardiac muscle action potential. The resting membrane potential of a ventricular muscle fiber is minus 90 millivolt. Here in this diagram, we can see that the action potential is divided into different phases starting from phase 0, 1, 2, 3 and 4. Phase 0 is known as initial rapid depolarization. When a stimulus or impulse reaches an atrial or ventricular muscle fiber, which was already in a resting state with a resting membrane potential of minus 90, there will be opening of voltage gated sodium channel leading to sodium influx. This phase is called initial rapid depolarization or phase 0. Because of the entry of a positive ion, the negativity inside the cell membrane is decreasing and finally it becomes positive, reaching up to plus 20. You can see from minus 90 it is moving upwards, it reaches 0, then it reaches plus 20. So the negativity is decreasing because of the entry of positive ion, that is sodium. Next is phase 1, that is initial rapid repolarization. See, when membrane was polarized, it was more negative inside than outside. During depolarization, that negativity changed to positivity due to sodium influx. When this positivity is returning back to its previous negativity, we call it as repolarization. It is returning back to the polarized state. So it is repolarization. Here you can see the phase 1 is called initial rapid repolarization. That is, the membrane is returning back to its negativity by sending positive ions. Here it is potassium, sending positive ions outside. So you can see the diagram, this is the phase 1. It is coming downwards from positive side, that is plus 20. It is coming downwards, that is it is returning back to its negativity by sending positive ions outside, by sending potassium ions outside, known as potassium efflux. So that's why this phase is called initial rapid repolarization, where there is closure of already opened sodium channel and opening of potassium channel leading to potassium efflux. Next is phase 2 or plateau phase. So you can see phase 1 happened for a brief period. That's because of the opening of L-type calcium channel immediately. So in phase 2, potassium was moving outside leading to potassium efflux, and calcium is moving inside leading to calcium influx. So this is phase 2. Here you can see almost a straight line. So there is loss and gain of positive ion simultaneously. So this balances the membrane potential. So here the membrane potential is constant. So you can see the phase 1, which is very brief, and this is the phase 2. Here the membrane potential is constant. That's why we get a straight line known as plateau phase, and this plateau phase is because of the balanced potential here. That is, the potassium efflux was balanced by calcium influx. Next is phase 3, that is final repolarization. So repolarization means, as I have already said, membrane potential is returning back to its negativity inside of the cell membrane. So it has to pump more positive ions outside. So during this phase, there is closure of calcium channel and opening of multiple potassium channel, leading to potassium efflux. So when more positive ion, that is potassium, is given out, the membrane potential returns to its negativity, that is minus 90, which is the resting membrane potential, and this phase is known as phase 4. So this phase of depolarization and repolarization together constitute the action potential. I hope you all have understood about the ionic basis of different phases of cardiac action potential. So the usual question is, write a short note on ventricular action potential or write the ionic basis of cardiac action potential. So you have to write the ionic basis of different phases, that is phase 0, 1, 2, 3 and 4, and you also have to draw a neat labeled diagram. Next we'll see the answer to a question. So what is the question? Why tetanus is not possible in cardiac muscle? So we know that it is possible in skeletal muscle, but in cardiac muscle it is not possible. For understanding the answer, you have to learn refractory period. So what is this refractory period? Period following action potential during which cardiac muscle does not respond to a stimulus. That is known as refractory period. And it is divided into absolute refractory period and relative refractory period. What is absolute refractory period? During phase 0 to half of phase 3 of action potential, cardiac muscle does not show any response at all. So whatever be the strength of the stimulus, it will not respond. This period is called absolute refractory period. So here you can see a diagram showing action potential of the cardiac muscle and its mechanical response, that is contraction. So this is contraction up to here, then relaxation. So you can see they have labeled from 0 to half of phase 3, the 0, then 1, then 2, then up to here, half of phase 3 of action potential. Then you can see here the full contraction, then initial 1/3 of the relaxation up to here. So this whole area, okay, this part is known as absolute refractory period. So if you give a stimulus during this period, even though the strength of the stimulus is more than the previous one, it will not produce any response. So the muscle will be contracting during this time. If you give a stimulus, it will not respond, and after contraction, this is relaxation. So beginning of relaxation, initial 1/3 of relaxation. Here also, if you give a second stimulus stronger than the first one, still your cardiac muscle will not respond. So up to here, there is no response from the side of cardiac muscle, even though the second stimulus is stronger than the first. So this period is known as absolute refractory period. Now what is relative refractory period? Period during which cardiac muscle can be excited if the strength of the stimulus is increased, and it extends from second half of phase 3, okay, second half of phase 3 to phase 4 of action potential and the lower 2/3 of the relaxation. So this is the relative refractory period. So you can see second half of phase 3 and phase 4, then the final 2/3 of the relaxation period.
So if you give a second stimulus having more strength than first stimulus during this period, it will respond. So if you give a stimulus during this period, it will respond only if the strength of stimulus is more than the first one. So that is relative refractory period. Okay. Now you think why tetanus cannot be observed in cardiac muscle. So what is tetanus? Tetanus is a state of sustained contraction due to repeated stimulation of muscles. So we require a sustained contraction for tetanus to happen. That is without a relaxation in between. Here in cardiac muscle, the refractory period is long. And from the diagram, we understood that a fresh contraction can only begin after the initiation of relaxation of the previous one. So a sustained contraction is never possible, because if the second stimulus is having a strength more than the first stimulus, the muscle will respond, but the subsequent contraction due to this second stimulus will be possible only after the initiation of the relaxation of the previous one. So even though the heart is responding to the second stimulus, it will be producing the contraction after the initiation of the relaxation of the previous one. So that sustained contraction is again impossible. So that is why tetanus is not possible in cardiac muscle, and that is very helpful also. How? As the heart has to function as a pump, it must relax, get filled up with blood, and then contract to pump out the blood. So a tetanized heart cannot do this function, because if it is tetanus, there won't be any relaxation in between, so that filling never happens. So it will be difficult for the heart to do this function, and if heart is not pumping out blood, means it will not be possible for the person to survive. So that's how this is important. I hope it is clear. Thank you.